Suppose that we have a 2-qubit register. How can we describe its joint state? Well, in the same way that the state of a qubit register is in a superposition of the two levels of the system, 0 and 1, it turns out that the state of 2-qubit registers is a superposition of all possible combinations of the first qubit register being 0 or 1 and the second register being 0 or 1. So, the general state of 2 qubits can be written as a linear combination not of 2 but of 4 states, which in the computational basis of 2 qubits will simply be 0, 0, 0, 1, 1, 0, and 1, 1. So similarly as before, we have a complex valued vector to represent the state. The vector just consists of the vector of probability amplitudes. So this means that a priori we need 8 real coefficients to identify the state. However, similar to the 1-qubit case, there are a set of constraints that these vectors need to verify. First, the state must be properly normalized, meaning that the sum of the magnitude squares must add up to 1. And just like in the case of a 1-qubit universe, in a 2-qubit universe, the global phase of the 2-qubit system is not relevant. Okay, so that means that the full description of a 2-qubit state requires us to specify 6 real valued parameters. It's going quite fast, from 1 qubit to 2 qubits. So this may hint at a problem which we will discuss in a moment. In any case, before we move any further, you might be wondering if we will discuss a Bloch sphere for 2 qubits. Well, it turns out that unfortunately there is not really a convenient graphical representation for more than 1 qubit. So we will not go into that direction. Before we proceed, I will introduce an operation, the tensor product. For our purposes, I will only define it operationally. Given 2 matrices, in this example vectors, the tensor product between them is the matrix that results by creating a block matrix with 1 block per entry in the first matrix, and each block consists of the corresponding element of the first matrix times the second matrix. Well, this is quite of a mouthful, so we can see here an example with 2 vectors, phi and psi. In order to obtain phi tensor psi, what we do is to create a block matrix with 2 entries. The first one consists of the first entry of phi, which is A0 times psi, and the second one of A1 times psi. So the tensor product is an operation that will be very useful for defining the states and gates of multi-qubit systems. Similar to the 1-qubit case, we are free to choose the basis of our 2-qubit space. Similar to what I did previously, one can construct a basis for the 2-qubit